Hi, this is Dr. S.P. Asaf from Mechanical and Industrial Engineering Department, IIT Roorkee. In the course of vibration control, now we are in the last module and the last lecture. And in this module, where we are discussing about the vibration measurement technique, straightway, we discussed about the basics of measurement technique, then we discussed about what are the dynamic parameters which we can measure, and through that we can characterize the basic vibration signatures. And you see here, when we are measuring the the dynamic parameters, we know that this entire measurement with these sensors or the transducers which we are applying there at the vibrating body, they are basically there in the time domain feature. So the information which is coming in the time domain, sometimes we cannot analyze accurately. So we need to transfer this time domain information into the frequency domain part using this Fourier series. And in the Fourier series decomposition, we know that there are various features which we need to, because you see here it is pretty easy now because the MATLAB functions are there and we can straightway convert this time domain to frequency domain. But the maths is saying that we need to check it out, that what exactly the waveform feature, whether we are talking about sine wave like the triangular wave or the rectangular wave, or whether we are talking about the square wave, what kind of waveforms are there, and then what is the corresponding mathematical functions in the Fourier series decomposition. And in the last lecture we discussed about the Fourier transforms when you have the non-periodic features in that. That means when you have any kind of abrupt change, means through the shock or the pulse like the impact form, or when we have the turbulence kind of signature, then you see here instead of just going with the Fourier series decomposition, we can use the short term Fourier transforms. And for that you see here with the using of in this f of t, which we are saying the Fourier signal, in this the alpha which was the coefficient, by changing the decreasing the alpha or by increasing the total time or by decreasing the time step, we can rather characterize these whatever the impulse features are there accurately. So you see here we discussed and all the part, and then we discussed about the numerical problem, that you see when we are just taking these the sine wave, or whether we are just talking about the square or the rectangular wave, triangular wave, then how by simply increasing the time total, means the time span, or by decreasing the alpha, how we can get accurately the variation features in that. So you see in this lecture now again we are going to discuss about the vibration measurement techniques, and in that you see here the filters part, which we are always being there, the filters are nothing but just it is a mathematical representation when there is a noise disturbance, or when we just want that these frequency peaks are the important frequency peaks, just to feature out that what exactly the kind of vibrating these masses or the characterizations are there, then we can allow them and we can restrict the remaining exciting features in the spectra. So the filters are basically designed according to the desired that what is the desiredness and what exactly the application parts are there in that. So frequency analysis implies the study of the signal distribution along the frequency axis, and on one side you see it is just showing the amplitude, that what exactly the amplitude of the vibration excitations are. So this frequency analysis has traditionally been carried out mathematically or by means of analog electrical filters, which are being constructed on the conventional electric components in that. So whether we are talking about the fast Fourier transformation or digital filtering, these are the key components nowadays in the digital technology. And you see primarily we need to apply these two, especially either FFT or the digital filtering according to our desiredness. So both make use of digitized measurement values, and each type of filter is absolutely named after its effect on the signal frequency spectrum. Like if we are talking about the low pass filter itself means you see here we need to allow the low frequency component, and then you see here whatever the high frequency components are there which has to be restricted. And correspondingly you see if we are saying the high pass filter, band pass filter, band stop filter, we need to define the ranges, that you see what is the frequency the range which is supposed to be allowed, or which frequency range is supposed to be stopped with these electrical filter design. So, if you look at that, you see in this diagram where it is clearly showing that we have a machine which is vibrating, and you see we have, say, right now we are saying that we have the accelerometer, and accelerometer is being capturing whatever the frequency excitations are, or this whatever the the vibration excitations are there in terms of, you see, the amplitude and the frequency. So, right now if I am saying that, you see, this is what my raw signal, in which you see it is a clear variation is there in the amplitude with the exciting frequencies. So, this is the total, we can say, the frequency spectras are there. Now, the first case when we are saying that the low pass filter, as per the name itself, you see here we can say we are basically looking in terms of amplitude with the frequency, means the initial pass. So, if you want to design this, that means, you see, this is what the width which is supposed to be provided by the electrical signal to allow the initial part, and the remaining part means the I mean to say that if I am just looking towards this part, this total frequency spectra. So, this initial feature of the frequency with the amplitude is being allowed, and the entire remaining part is being restricted by that. So, if I am just looking to the actual situation when this signal is being passed through this we can say low pass filter, then I can say that I have, you see, this is what my frequency spectra with low pass filter, and this is clearly showing that, you see, at the low frequencies how the variations are there, like in the frequency, exciting frequency with the amplitude. Second, when we are saying that the high pass filters, the high pass filters means now basically our the analysis range is in the high frequency zone. So, when we are talking about high frequency zone, then you can see that the second figure which is clearly showing that, you see here, this part, the initial part is absolutely restricted, and then the the frequency component which is to be allowed to analyze, this is what you see, which is falling in the high frequency part. So, this is, you see, the high frequency, and if I am looking to the actual raw signal, then we will find that the initial feature means the initial peaks and the variation is being restricted, and the final part is being allowed now. So, this is, you see here, if I am looking to the main part, this final part is being allowed, and which can be shown here. Now, when you see, when we have such kind of, say, the pulse in the impulsive form, or such kind of, you see, the any defect feature is there in, and we are getting some kind of the spatial we can say frequency components during the running part. So, now we need to bend that part, that now this is what, you see, I want to analyze that why it is showing a different nature as compared to all other my signature. So, then you see here we need to capture the middle part, we need to bend the frequency ranges, and that frequency ranges is being allowed. So, that part we are saying that the band pass filter. So, band pass filter, that means, you see, the initial feature is being allowed. Say, you see here, if I am just talking about this part in the main structure, somewhere you see this exciting peak is high. It is a normal part, but this peak excitation is at its highest level, maybe because of some defect, maybe because of, you see, some sudden excitation is coming. If we want to analyze this, that means, you see here, we need to allow this range that you see within it is being falling at the frequency and with the corresponding amplitude. So, that means, you see here, if you look at this amplification part here, you will find that this is what you see being allowed, and the remaining means the lower and higher frequency regions are being straightway stopped there. So, in this raw signal, you see here, this is what my now the signature, vibration signature, which clearly shows that yes, in this particular frequency region you have this kind of frequency spectra. Or if I just reverse that, if I know that because of some irregularities, or because of some some kind of impactive impulsive forces, you see here, I know that I have some kind of the non-periodic, or I have, you see, some kind of the adaptive changes are there in my signature. And later on, you see, once the things are being overcome, then I have irregular phenomena. So, now if I want to stop this, the next filter is the band stop filter. So, band stop filter is now, if you look at the nature of the band stop filter, that means, you see, the band which we defined can straightway stop this frequency component, and you see the remaining feature, if you look at the real nature of the signature, or this real signature of the vibration, the nature itself says that this peak is now absolutely omitted, and then you see here we can say that the entire spectrum is being just varying whatever the required features are. So, either we are talking about low pass, high pass, band pass or band stop, we can clearly feature our response whatever the responses are there in the signature analysis, and we can analyze those corresponding whatever the vibration signatures are there. So, as we discuss the filter type which is most common in we can say is the low pass filter, and such filters are often used as the input to a measurement system to filter away the frequency components higher than those to be analyzed. So, these removed components would be otherwise introduced the error during the digitization process, and you see in the digitization process by this contaminating the low frequency components, or we can say the aliasing effect. So, when we are doing some the digital figures in that, so during this entire process we know that this whatever these low frequencies which are coming in that, the anti-aliasing features, the features are being incorporated that. So, we need to remove this. So, that is why generally we are saying that the low frequency components or the low pass filters are pretty common in their application, and during this entire process when we are removing this, we can say that aliasing effect is pretty common in this part. So, we are saying that you see the band pass filter, this is what you see the the third one. In that, the ideal band pass filter which I am going to show you is just suppress the components at the all frequency except those which are being lying within this bandwidth. So, we need to now define the bandwidth, what is the width is there through which the entire you see the frequencies are being passes from these filters. So, in practice you see here the edges of band have certain slope. We know that you see when they are being passing they have the slope, and which implies that the frequency components immediately outside the pass band are not completely eliminated, because they are not the squared one. When they are the squared one, then we can say that you see whatever the frequency components are there which are being passing through that, they can be completely recovered, they can be completely eliminated. But since they have the curved shape, so from side you see here these things are being passed through. So, a common way to define the upper limit where you see the curved feature is there and the lower frequency you see here limit of the band is to indicate the frequency at which the signal can be reduced by 3 decibel part, 3 dB. So, you see here if you are just looking to the exact shape, the ideal band pass filter with these the we can say this indefinitely step cutoffs. So, we have you see the initial frequency, the lower frequency and upper frequency range, and if I am saying the bandwidth is this Fu minus Fl, the upper band and lower band. So, this is the square form of this. So, if this is what you see the ideal form, but whenever we are talking about the real the wave form of that, then the real filters have to be there with this imperfect cutoffs. So, you see we can say that when we are just talking about this, we have you see the curved feature of our signal part, and when we just want to use this bandwidth there, we know that if you are just going with this part this the slant part which is being there, you see here it's a kind of you see the error in that, because this is the imperfect cutoffs are there, and the upper and lower bounding frequencies are then defined by those frequencies at which the filter is reduced the signal by 3 decibel. So, if we are just looking at that point, if we are reducing the signal by 3 dB, that means you see here up to almost we are in the perfect zone where we can say that the real filters can pass this much bandwidth is there. So, the band pass filters are are named according to how the bandwidth varies along with the frequency axis. The frequencies with the bandwidth that do not vary along the frequency axis called the constant absolute bandwidth. That means you see we have the CAB filters, in which there is a clear absolute you see the bandwidth are there and they are just constant all along the frequency axis. But a filter with the bandwidth which is proportional to the center frequency Fc is called the constant relative bandwidth. So, you see here if we are just our base is the reference frequency, means the central frequency, and then the filter is being decided based on what is this side, the lower side and upper side. We are saying that this is the constant relative bandwidth, and when you see like we are not changing the bandwidth along with the frequency axis, we have constant absolute bandwidth. So you can see that we have constant absolute this these bandwidths are there, in which we have the absolute features are there. So if you look at that, they are absolutely like varying with these like say if I have the bandwidth of 100 hertz. So we can right away like start from say like this is what the scaling part is there, this is what you see in between, that what exactly like the bandwidth gaps are there, and this gap will be constant you see. So if I am just going with this like say 5K to 1K, I can simply say that I have like the bandwidth is 100 hertz, or even you see when I am just going from the 9K to like the 900 to 500, sorry this 9K to 5K, then again you see I can say that I can simply remade this part as the constant bandwidth. So here the bandwidth is not varying with the frequency axis, and it is typically presented with the linear frequency axis. So whatever the frequency axes are there and the corresponding peaks, the peak is repeatedly like occurring at the constant frequency, and you see here there is no variation in the nature of the excitation peak as well. And if you are just talking about the variable, means now you see the central frequency is first being calculated, and based on this central frequency now the other widths are being like considered there. So we can say the bandwidth is now nothing but equals to like this square root of like the 2 minus we can say 1 over square root of 2 whole cube of that into this central frequency. So here this is what my linear frequency ranges are, and in between you see here the bandwidth is calculating based on the central frequency and corresponding width accordingly. So now you see like if you are just going to this CRB, which is nothing but the constant relative like the bandwidth filter, a bandwidth that is like is a certain percentage of the centralized frequencies, and it is typically presented with the logarithmic scale. Because of the logarithmic scale, the stack in the figure do not get like we can say the wider, and when we are moving, as previously I shown you, just we need to move along the positive axis of x. So we can say that this figure is like is called the third octave band filter, and has the bandwidth is almost like we can say the 23% of the central frequency. So octave band is to be designed in such a way that like we are reducing the signal by 3 dB in like upper and lower, and once you calculate the central frequency, then like the variation of this is the 23% of either. So when we are talking about the third octave or the octave band filter, the third octave and octave band filter are nothing but the constant relative bandwidth filters, and widely they are using in this vibration part, in which the main part is coming that what is the central frequency which we needs to be standardized there, and then you see like we can simply configure the other two part. So both type of filters are named with the band number, as I am going to show you the table, and more often by like their central frequencies they can be varied accordingly. So we can simply see now that each octave band spans, or 3 octave band you see like in each octave band the span of 3 octave band bands, which explains like the name of this category of the filter. Means you see here in each octave band now there are in the entire span there are 3 octave bands which are being there within that. So if you look at this, you see like these basically on the definition of this third octave and the octave band filter. Now we are absolutely say in octave band filter my lowest frequency is absolutely that the FL is nothing but equals to the 1 by square root 2 of my central frequency. And when I am now categorizing this frequency band with the 3 like this part, so certainly my lower band under the third octave band filter FL is nothing but equals to 1 of like square root of 1 by 2 square root of like to the power 1 cube, means 1 by 2 to the power we can say like like the cubic features are there into FC. So FC divided by square root of 2 to the power 6. And similarly you see if I am going for the higher frequency, again I need to go right from the central frequency towards that. So again this is nothing but equals to the FU is square root of 2 into this, because now I need to go on the upper side, so it is into central frequency. And similarly, if I am going towards the third octave band filter with this central with this upper limit, so my upper limit exciting frequencies are nothing but equals to the Fc central frequency into square root of 2 to the power 6, means 1 by 6 I can say. And then you see here, based on this upper and lower limit in both octave band and third octave band, we can calculate the bandwidth. So the bandwidth in the octave band filter is nothing but equals to Fu minus Fl, as we know that. So we can say it is nothing but equals to, as we discussed already, square root of 2 minus 1 by square root of 2 into Fc. And similarly, you see we can calculate the bandwidth there in the third octave band filter. So again you see it is nothing but equals to Fu minus Fl, which is nothing but equals to the square root of to the power 6 minus 1 by 1 by square root of 2 to the power 6 into Fc. And even we can calculate the central frequency in both the cases. So the central frequency in both the cases is nothing but equals to Fc is equals to square root of FLFU, means this lower and upper frequency into square root, or even for third octave band also it is nothing but equals to square root of FL and FU. So this is what you see the clear definition, where you see the first, once we define the third octave band and once we define the octave band, we can make a clear relation, because in the octave band now we can separate the 3 different segments, and you see again same, every segment is showing the octave band features only in the 3 forms. So now you see here we can standardize the central frequencies, upper and lower frequency limit for third octave band and octave band filters with these like the octave band. So if we now the shading features are there. So if I am just talking about the band number, say I have the band number 1, I can see that the central frequency can be of 1.25 if this third octave band is almost 1.12 to 1.41. And then you see here when we are increasing the band number, say 2, 3, 4 or whatever you see, say if we are at the band number 3, our central frequency is 2 and the third octave band means you see FL minus FU is 1.78 to 2.22, and we can get you see the octave band filter for this is 1.41 to 2.82. That means you see here we can straightway start from the minimum for these, right from band 1, we can say straightway we can say from band 2 to band 4. For this you see here the third octave band filter is being designed, and the frequency for this is 1.41 as the lower and 2.82 as the upper frequency. So similarly you see we can go for 5 to the 5, or you see even 5, 6, 7 for this, and then for 8, 9, 10, and then you see we can go for the for this 11, 12, 13. So for these part especially we can, all for 3 parts we can go and define that what could be the the central frequency, what is the we can say the octave band filter part especially, where you see the third octave band is there and octave band filters are there. So for individual part you see here, means for individual band number the octave band filters and third octave band filters are to be designed, and you see here in these tables particular we can go up to you see the band numbers almost up to 43. And there you see for even when we are talking about say 41, 42, 43, for 41 we can say you see the central frequencies are 12500, and then you see here we can simply define the third octave band. Say for first 41 band number it is 11200 to 14100, for 42 it is 14100 to 17800, and for 43 it is 17800 to 22400. And when we are talking about the octave band filter, in which you see a lower and upper limits are there for band number 41 to 43, then we can say that it is for 11200 to 22400. So this is almost you see we can say once you define the central frequencies, in between you see here the both the the bandwidth can be decided, and then you see here accordingly the filter can be designed for many number of you see the band numbers. So you see for 43 we have shown here in this that you see how we can design those features together. Now in the another section we are now going to discuss about the addition of frequency components. So there are you see various ways through which we can describe the signal distribution in frequency dimension, or we can say in the frequency bands. And when we are talking about the narrow bands, they are simply giving the detailed information on the distribution of energy, and in that you see here with the relatively low amplitude in each band. So you see the narrow bands are always just discretized those entire informations within, you see like that how the distributions are there at those like the lower amplitudes. So you see if we just want to show this part, then this is what it is, you see here, this is the actual waveform which is being there, you see here. And if we are talking about the narrow bands, this is what the narrow bands are there, and they are absolutely showing that at the lower amplitude what is the like the energy distributions are there. But the key feature, if we are using the octave band, so for the octave band you can see that this is being starting from this phase, and then you see this is for this way. So you see here when we have these say the variation like that, the octave band is starting from this to this. And again you see when again you see like when it is going deep and then the variation is there, the new octave band in the second form is starting from here to here. So this is, you see here, the second form. And then you see the next octave band, because again you see there is a drastic change. So here we are again putting the octave band, and then you see up to this, before the narrow band this octave band is there, and then you see like all the variations are there. So this is my octave band for the fourth octave band. And when we are putting the third octave band in individual the octave band, you see here, so we have, you see like this these octave bands where the variation, then again an octave band, and then again octave band. So now this entire octave band is to be divided into 3 equal segments, where the featured are being taken in such a way that we can classify these the bandwidth for whatever the variations are there. So you see here for this octave band also there are 3 octave third octave band, in that there are 3 components, this and this and this one. So they are simply showing that how the variations are there. So you see here, and like as we discussed, you see with the octave band and with the third octave band and with the narrow band, we can simply capture that what is the amount of energy which is being there during excitation, and how much energy which we just want to pass, and we just want to see that the frequency band, upper and lower frequency band, how they are being varied with these kind of signals. So now you see in this particular the same sound spectrum which I was presented there with the narrow band, third octave band and octave band, and we know that the bigger bandwidth, more frequency components can be contributed to any band, and they are always giving the higher levels. So the this logarithmic feature of the frequency axis can simply causes these constant relative bandwidth filters to have the same apparent width per band whatever over the entire spectrum. And when we are considering the constant amplitude bandwidth with their fixed band, you see along with the axis, and when the fixed bandwidth are there over the entire spectrum, they are appearing to grow more dense as the frequency is being increases. So that is why you see when we just want to see the specific or the discrete frequency features, certainly we are always going with the CRB, the constant relative bandwidth. And when we know that, you see there are not many number of frequency peaks are there, or the spectrums are there in the entire vibration signature, then certainly we are going with the like this CAB type of filters. So you see here we can say that when we just want to calculate those things, we can simply use, you see like that what exactly the total pressure levels are there in this. So we can say the total like the sound pressure in that is the summation of all these, you see the Pn square, right, from n equals to 1 to this, means we can simply calculate with the individual frequency excitations, we can sum up and we can calculate the total in our frequency band. So we can say that, as we already discussed, the sound power is nothing but equal to 10 log like summation of all these power on the basis of 10. So it is 10 to the power L Pn divided by 10, because you see here now when we are talking about like the numerical problem, this one say when we have this 1000 hertz octave band, which includes, you see 800, 1000 and 1250 third octave bands. So within this octave band now 100 hertz, now we have all three 100, 1000 and 1250 third octave band. We need to find out the octave band level if the third octave band levels are 79, 86 and 84 dB respectively. So now you see our sound level power, you see, which are simply we want to calculate this, the total band level. So this is nothing but equals to LP equals to 10 log. Now you see here 10 to the power, now we have this is 7.9, this 79, 86 and 84 already third octave bands are there. So, we can say 7.9 plus 10 to the power 8.6 plus 10 to the power 8.4, and when we are calculating this, this is almost nearly equals to 89 dB. Now, we are going to take the last example where we have a car model, say a quarter car model, and you see we just want to find out the dynamic properties like using like the vibration features, and the model is greatly simplified based on the assumption that the car has the vertical motion, and that can be described using the point mass model, in which you see the mass of the car is uniformly distributed on each of the four wheels. So, you see here we are simply assuming that through the center of mass, the car can be divided into 4 equal segments, and every segment is being supported with the tire part, because the 4 wheels are there and you see the entire wheel is being supporting. So, that is why we generally are saying that this is a quarter car model for this, and the quarter car model consists of 2 masses M1 and M2. So, you see here we are saying that the quarter of the car body mass above which the suspension is there, that is my M2, and the complete wheel mass is my M1. And correspondingly we can say that the mutually coupled spring damper system is there. So, we can say K2 and this D2, they are simply showing the compliance we can say the this spring and the damping features. While you see we can say when the wheel mass which is finally coupled with the roadway via the spring K1 is being compliance with the tire itself. So, we can say the quarter model, which can be clearly shows here that we have you see the M2 which is being here. So, as we already discussed that the the complete wheel mass is my M1 and M2 is the car body mass. So, this is what you see, the car body mass is there, 1/4 of the car, which is like the car body mass, then it is being suspended, and you see during the suspension we have both the K2 and dV2s are there, which is being associated with the car body mass and with this wheel mass. So, this is what my wheel mass M1 is there, and this is what wheel, and below the wheel we know that you see with the surface road surface contact we have you see the damping, and you see these spring properties with the tire deformation. So, this tire is now providing the stiffness feature and the damping feature, just like you see the K1 and dV1. So, from the perspective of vehicle dynamics, it is of the great interest to study the displacement Z1 and Z2. You can see that we have a clear Z1 and Z2. From the when the car is traveling, there is a clear excitation of the wheel and the body suspension with this, and the profile of the road surface relative to this elevation. Now, you see here the profile, when we are just talking about the profile, we do not have a clear like the smoother road surface. So, that means you see we have a time dependent displacement from the ground, and this is what the the zeta of t. So, with this now our interest is to now find out the mass, stiffness and the damping matrices of this first the quarter car model, just to see that how the formation of these matrices are. And now, the data which we can straightway use for the typical passenger car, say M1 is our 20 kilogram, M2 which is of the wheel is just 20 kilogram, the entire body mass of the vehicle means 1/4 of this is 350, not the entire, means the 1/4 of that 350 kilogram. The K1, the stiffness associated with this the tire one is 200 kilonewton per meter, and K2 which is associated with this body to car suspension, they are of very less, you see 20 kilonewton per meter. The D1 is not there because you see the damping is not being acted along with the tire. So, we are assuming that there is only the restoring forces are being there when they are being excited from ground to tire itself, and then D2 is given as 1 kilonewton second per meter. So, this is one. We need to now determine the undamped eigenfrequency of the model, and also you see if you are assuming that the car travel on the road surface with a sinusoidal profile now, and that sinusoidal profile having the wavelength of 10 meter, then we need to find out the velocities at which the severe vibration of the car are to be expected. So, this is something you see a very typical vibration problem, and we need to formulate using this part. So, we can say that you see how we can put those things. So, first thing, the mass, stiffness, damping matrices that can be straightway get with the usual terms. So, M like this is like along the diagonal they are being symmetric. So m1 0 0 m2, k is k1 plus k2 minus k2 k2 and this one, and this is what it is. Now if you want to calculate the undamped frequency, eigenfrequencies, we can calculate to see the k1 plus k2 by 2 m1 plus k2 by 2 m2 and then the square root of both the square plus you see here like k2 square and you see minus k1 k2 over 2 m1 m2. So when we are keeping those values, we can get straight away the first natural frequency of this is 104.91 radian per second. And similarly you see here we can get the omega 2 because you see it is a 2 degree of freedom system. So again it is being there along with the k2 and k1. So we can simply put those values because k1 k2 are given to us and m1 m2 is there with us. So we can calculate the omega 2 as 7.26 radian per second. So this is what the excitation frequencies are there at the for the wheel and for the body mass. So correspondingly we can say that the F1 will be excited at 16.7 hertz and F2 like means the body the car body mass at the 1/4 will be excited at 1.16 hertz. So that is what you see one formation in how do we calculate this, but the main feature is coming when the like the car is moving at the constant speed and we have a sinusoidal road surface profile. At the lower end you see and they are being coming to the our tire part for which the spring K1 is going under the sinusoidal vertical motion say Z0. So now you see we need to assume that that Z0 which is nothing but you see the epsilon t which is given the question is nothing but the epsilon 0 sin omega t, because all these features are being there all being like feature of the road is being coming to the vehicle. And even we can like explain this in the complex form. Generally we are using the Z0 is like the epsilon 0 e to the power I omega t. So we can calculate the circular frequency based on you see what the wavelength is giving of the road surface through which you see this sinusoidal feature of excitation is coming on the vehicle. So when we are trying to do, we know that say the given speed v is there for car which is passing through the certain number of wavelength on the road surface profile per second. So that number, that means you see the frequency f can be calculated from the ratio of the distance travelled by the vehicle in per second. That means we can say that the frequency is nothing but equals to the velocity v divided by the wavelength lambda. So when the car is driven at the speed that causes the roughness induced you see the exciting frequency must be equal to one of the two eigenfrequencies. So we can say that the strong vibrations can be expected at these two exciting frequencies are there. So we can calculate the critical speed. V critical is nothing but equals to lambda into f1 and lambda into f2. The lambda is given, the wavelength is given as 10 and exciting frequency first was coming at 16.7. So the first is 167 meter per second and second like the critical where the V critical at 2 part. So lambda into this f2, lambda is 10 and f2 is 1.16 exciting frequency. So we have 11.6 meter per second. So this is what the speed, the critical speeds are there where we can expect the use like we can say vibrations at that. So this is you see the last numerical of this course vibration control, in which we discussed almost you see all types of signatures, signature analysis using the filters, data acquisition systems, fast Fourier transformation, time domain frequency analysis, and for developing the entire course we have used various references, and I would like to quote those, and I have already quoted in many of you see the citations wherever it was there, but also you see here especially we are so thankful to the from the book which we have adopted in our one of the MOU with the KTH Sweden and IIT Roorkee for developing the courses and just flourishing this awareness about the sound and vibration to this Indian conditions. So that MOU was under you see like the Eurasia project. So that book was provided by them, by Professor Metzberg and team. So we are so thankful, and we are simply citing this Fundamentals of Sound and Vibration by KTH Sweden book. That is one of the basic book. We also used you see like the main core books of the basic vibrations, like the Fundamentals of Mechanical Vibration by Kelly, the Fundamentals of we can say the vibrations by Marowich, and then you see like the Mechanical Vibrations by S.S. Rao, Theory and Practices of Mechanical Vibrations by J.S. Rao and Professor Kshitij Gupta, Handbook of Noise and Vibration Control especially by Malcolm Crocker, and also you see here the active vibration control by we can say by this Nadir, Professor Nadir there in like the Clemson University, and also Professor Inman, Daniel Inman, the vibration control. We have also like referred those various there, and we are cited there. And also lastly but not least, the Wikipedia sites are also providing some kind of the basic informative features, and we have taken the e-materials from that itself. So thank you very much from the team like through which we generated those courses, and either from the web or the video part. Thank you very much.